All right, we're going to review vectors and parametrics. The formulas and the information you need is at the top of the note card. Example 1, the position of a particle is given by an x and a y equation defined on the interval from 0 to 2 pi. Part A asks us to find the velocity vector. All right, you record the answer here in the space between A and B, but with my prior experience with this page, okay, I can't write in this space, so I'm going to actually put the answer for part A right down here. But you just put it in the appropriate place. Okay, so the velocity vector is going to be the derivative of the x equation, which is cosine of t, and the derivative of y, which is using chain rule -2 sine 2t. And this is the notation that we use, okay, to represent a vector. All right, for question B, for what values of t is the particle at rest? All right, well, if the particle is at rest, it's not moving. Okay, the velocity would be 0. But in the context of parametrics, we're not just dealing with one velocity equation, we're dealing with two. We're dealing with x prime and y prime. So for the particle not to be moving at all, horizontally or vertically, okay, then we have to set both derivatives equal to 0 and find the times that they have in common at which that occurs. Okay, so I'm going to start with dx dt. Okay, let's find where cosine of t equals 0. Do an arc sine on both or arc cosine, sorry, on both sides. So bring in the inverse cosine. Thinking about the unit circle, between 0 and 2 pi, the x coordinate will be 0 at pi over 2 and 3 pi over 2. Okay, beyond that will be outside of the interval of 0 to 2 pi, so I'll stop here at these two solutions. Okay, to be at rest also vertically requires that dy dt equals 0. Setting y prime equal to 0 and solving. Okay, divide both sides by -2. Well, that still results in 0. Bring in an arc sine on both sides of the equation. All right, so at what angle is the y coordinate 0? Well, that would be at 0, pi, 2 pi. Okay, you might be tempted not to go beyond 2 pi. However, remember we still have to divide by 2. So if I generated another value here of 3 pi, when I divided that by 2, I'm still within the interval from 0 to 2 pi. And also want to put 4 pi here, because half of 4 pi is 2 pi, and that's still within 0 to 2 pi. Although 0 to 2 pi may have had parentheses, in which case I have to exclude them. But we'll worry about that in a minute. Divide everything by 2, so that's still 0. That's half pi. This would be pi. 3 pi divided by 2 is 3 pi divided by 2, and this is 2 pi. So actually what we have in common here are these two time values. Okay, so that would be the answer. At half pi and 3 pi over 2. Okay, we're not going to answer question C. I've never seen that asked. The question here is, can you take the two given equations x and y and eliminate the parameter? Okay, we're not going to take the time for that. All right, example 2 switches gears. Now we're talking about a roller coaster. And for this particular problem situation, we're given the rate of change of the horizontal component and the rate of change for the vertical component. We're given x prime and y prime. Defined on time values between 0 and 10. It does give us an initial condition, meaning that the roller coaster is at a height of 1 meter at time equals 0. And actually for these two questions, A and B, okay, we don't need that information. Okay. Not all of the formulas at the top of this note card are going to be used. Okay, we've just picked out two here. Part A, find the time at which the car is at its max height. Okay, that's a maximum question. So we're looking for where the derivative is 0. And we're talking about the parametric context here. So that would be where y prime divided by x prime is equal to 0. Okay, so for me to find this answer, the time at which the car is at its maximum height, okay, I need to figure out where this fraction is equal to 0, and that is actually where the numerator is 0, but not the denominator. So where is dy dt equal to 0, okay, but not the denominator? Okay, so we're going to take the y prime equation and set it equal to 0. Now, you might not have noticed this, but there should be parentheses around 20 minus t. That's quantity 20 minus t times sine of t. Okay, this is strictly a calculator question, so I would encourage you to go to your calculator, enter this into y1, set a window from x min 0 to x max 10, and observe where this slope graph goes from positive to negative. And actually what you're going to see is there's a couple of times where this graph goes from positive to negative. And you want the first time. So you might be thinking, well, why not the second time? Well, at the first time, the roller coaster actually has traveled further, as indicated by the area under that graph from time equals 0 to that first x-intercept. Okay. If you looked at the next time this equation passes through the x-axis from positive to negative, the value of the integral that represents that next loop, if you will, is not as great. Okay, that space is less, indicating it didn't go as high. Kind of interesting. I encourage you to graph it to see, what I'm talking about. All right, so when I find that time intercept, it's at 3.0239158 seconds. That's the time that the car reaches its maximum height. Okay, you might want to just double check and plug in this time value to x prime to make sure you don't get 0. I feel certain you're not going to get 0, but it's always a good thing to double check. All right, part B, let's find the speed. We have a formula for that. This is going to get cumbersome in the calculator, so it might be good to kind of do parts of it and then go put it all together. Okay, but you certainly want to show the setup first, and then how you deal with it in the calculator is certainly up to you and how you feel like you can manage it. Okay, I'm going to evaluate the first derivative, x prime, that's given up above, okay, at this time. And then I'm going to square it. And I'm going to add it to y prime evaluated at that same time. Okay, so just take this time and go back up into the problem and evaluate both x prime and y prime, and then complete the necessary calculations of squaring, adding, and square rooting. Okay, like I said, it becomes pretty cumbersome. Hmm, 6.027, and let's see, I had another decimal. Where to go? It's 6.02766. And just for good measure, 37 meters per second. Okay, I encourage you guys to at least attempt to calculate this and see if you can come up with this speed. Okay, as a little hint, a little shortcut, let's just kind of think about this. Maybe some of you guys already have. If you're going to calculate the speed, just look at this piece right here. Well, if I take y prime and I plug in this time value, I should get 0. Because that's how we got the time back up here in part A. We set the derivative equal to 0 and find the time at which it was 0. So if you think about it, this right here is just going to result in 0. So all you really have to do is calculate this right here. Find this value, okay, square it, and find the square root. A little bit of a shortcut in this particular situation. Okay. All right, for this particular note card, we weren't asked to find an acceleration vector. We weren't asked to find a total distance, which is the arc length, to set up that integral. We weren't asked to find the slope of the curve, nor were we asked to find the second derivative. But I still encourage you to look back up at those and refresh your memory about those particular formulas. All right, I'm going to go to the last note card, which is note card 28, and the topic there is arc length. Okay, and so for that last note card, it's arc length not with parametrics, but just with functions. Okay, so if you look at the top of this note card, Okay, you can kind of observe what the arc length formula is in comparison, arc length formula is for parametrics in comparison to the arc length formula for functions. All right, so we'll look at note card 28. All right, so we've got the formula up here in front of us. This is with respect to x. Remember, there's also another formula we can use, and it's with respect to y. Okay. I don't know why it's not present. I think if I were you, I might want to write it to the side here. Or not. Or not. It seems like it wants to go up here, but I would put it right here. Okay, so for arc length with respect to y, you're going to go from c to d. Square root of 1 plus, okay, and this would be some equation in terms of y, and we'll square that, add it to 1, and it's with respect to y. So we'd have to have both equations, or at least the equation, not both, sorry, the equation x equals in terms of y. Okay, example 1. All right, we're just going to set up an integral to represent the length of y equals x cubed on the interval from 0 to 5, and then use our calculator to find the length of the curve. Okay. All right, so our limits are 0 to 5, square root, 1 plus the derivative, 3x squared, and we're going to square that. All right, if you want to do a little bit of cleanup to avoid some of the parentheses, that might not be a bad idea. 1 plus 9x to the 4th dx. Okay, one less set of parentheses might be helpful. All right. So what you're going to do is store this into what you might want to actually store the square root of. This whole thing would go into y1. And then when you go to the home screen to integrate it, all you have to do is dump in y1. Right. Using the calculator, this is what you end up with. All right. Part 2, set up an integral to represent the length of this graph on the interval from 0 to 3. Find the length without a calculator. Oh, come back. 1 plus, okay, don't come back, 3. 1 plus, and there should be, let me write the function over here because I see it didn't, okay, I guess it wants it up here. Okay, it's 1/2 parentheses e to the x plus e to the negative x. Squared in terms of x. Okay, so it wants us to actually calculate this without a calculator. So what's going to happen is once you square this and collect it with 1, and refactor, it's going to refactor into a quantity square, because the only way you can do this by hand is if you get underneath the radicand, after you clean this up, is if you get a binomial square so you can take out one of them to integrate. Okay, there's a lot of space on your note card for this problem. I'm not going to take video time to go through that handwork. Okay, so at the very end though, when you do that, a lot of algebra. Okay, the final answer is this right here. Okay, and if you're interested, we could do that together in class, but for this video, that would just take way too much time. All right, problem number 3. Okay, we have a choice. Okay, so the length of the curve, so let me kind of put that work down here if it lets me. I don't know. Maybe I can try it over here. Okay, the note card's kind of a mess. Having trouble trying to get it to stick anywhere, so we're still on 3. But I think I'm going to have to do the work down here, and the work for 4 is just going to have to follow this work. All right. Okay. So we've got the integral from 0 to b. Oh no, stay. 1 plus. Okay, and I need the derivative of the natural log of secant x. So this is the function we want a piece of, a little length of. To find the derivative, oh goodness, it's going to be 1 over secant of x times the derivative of secant x, which is secant x tangent x. So a good review of some of our trig derivatives. When you clean this up, you're going to just have tangent of x. Okay? So the derivative is tangent x. Okay, looking at the choices, that's not there, but we can do a little cleanup. So this would be 1 plus tangent squared. Okay, and I know you likely don't remember, so let me remind you that 1 plus tangent squared is a Pythagorean property from pre-cal. That's equal actually to secant squared. You might remember that now, secant squared x. Okay, I'm looking for the choice. If it's there, it's not, but I can square root that square, and so the final answer for this one is just the integral from 0 to b of secant x dx. And that's going to be choice A. Kind of an interesting problem. All right, so hopefully this work on you is up here. Okay, let's look at 4 then. Oh, pretty straightforward. I think outside of the context of this problem, I'm going to go ahead and differentiate. So y prime, 3/2 x to the 1/2, or 3 squared of x over 2. Arc length, 1 to 4, our x coordinates. Square root of 1 plus the derivative squared. Okay, before I go to the calculator and type this in as y1, including the square root, I'd probably do a little cleanup. This would be 1 plus 9x over 4 if I were to square that quantity. Okay, and running out of room here, I think, space. No, I have a little bit. Okay. If you did the calculations on this, this is the value that I got. I encourage you to go ahead and attempt to do that with your calculator to make sure that there's no issues with the keystrokes. All right, so that was parametrics and then arc length as well.